Hello, cosmic enthusiasts and curious minds. Welcome back to our channel, where we dive into the mysteries of the universe. Today, we're tackling a headline-grabbing topic, the James Webb Space Telescope, JWST, and its recent measurements on how fast the universe is expanding. This discovery has sparked a lot of excitement, but also a bit of controversy. Stick around as we unpack why this matters and what the big problem really is. The James Webb Space Telescope has unveiled a startling revelation about the universe. It's expanding at a pace that defies our best predictions. This groundbreaking finding confirms a profound cosmological enigma known as the Hubble tension. Essentially, the universe is expanding much faster than anticipated, and scientists are baffled by the discrepancy. This revelation is crucial as it underscores a significant flaw in our understanding of the universe's expansion. Previously, astronomers speculated that the observed inconsistencies might stem from technological limitations, issues they hoped would be resolved with next-generation observatories like James Webb. However, instead of providing clarity, the new data from Webb has deepened the cosmological crisis. It suggests that there's a critical element missing in our calculations or observations, intensifying this mysterious tension. So, what exactly is the Hubble tension, and why has it become a pressing issue for astronomers? What did the James Webb Space Telescope observe that confirmed this cosmological crisis? Most importantly, what new physics might emerge from solving the puzzle of the Hubble tension? To grasp the magnitude of the biggest crisis in cosmology, we must travel back in time a century to the 1920s. It was then that two astronomers, Harlow Shapley and Herbert Curtis, found themselves at the center of a momentous argument now referred to as the Great Debate. The crux of their dispute revolved around the size of the universe. A simple yet profound query: was our Milky Way the entirety of the universe, or did other galaxies exist beyond it, suggesting a much larger cosmos? This question might seem bizarre today, but back then, the prevailing belief was that the universe was synonymous with the Milky Way. Although we had already captured images of other galaxies like Andromeda, these were mistakenly thought to be mere star systems within our own galaxy, referred to as spiral nebulae instead of galaxies. Thus, the debate centered on whether these spiral nebulae were internal features of the Milky Way or vast, independent galaxies like it. Shapley argued that the Milky Way spanned about 300,000 light-years and encapsulated all known star systems, effectively making it the universe itself. Curtis, on the other hand, contended that these nebulae were indeed separate galaxies, suggesting a universe far more expansive than previously imagined. Far, far away in time, on April 26, 1920, a pivotal debate unfolded, a clash of visions that would challenge the very concept of the universe's scale and the true nature of nebulae. Known as the Great Debate, this event did not yield a definitive answer on the night it occurred, leaving the astronomical community still divided. The resolution to this celestial conundrum wouldn't come from the arguments of either Harlow Shapley or Herbert Curtis, but from the groundbreaking observations of another visionary, American astronomer Edwin Hubble. In the 1920s, armed with the era's most powerful telescope at the Mount Wilson Observatory, Hubble embarked on an investigation that would transform our understanding of the cosmos. He focused on the Andromeda Nebula, which was widely believed to be a part of our own Milky Way. Hubble's attention was particularly drawn to a specific Cepheid variable star known as V1 within Andromeda. By measuring the distance to this star, Hubble made a startling discovery. The distance was approximately 1 million light-years away, nearly 3 times greater than Shapley's estimate for the entire Milky Way. This revelation supported Curtis's argument. The spiral nebulae were not mere components of the Milky Way, but were in fact vast galaxies in their own right. Although Hubble's distance estimates were conservative compared to what we recognize today, his work definitively showed that the universe was far more expansive than anyone had previously imagined. This discovery opened a new chapter in astronomy, fundamentally altering our view of the universe. As Edwin Hubble delved deeper into the mysteries of the cosmos, he stumbled upon a pattern that would soon unlock one of the most intriguing puzzles in the universe. Observing galaxies far beyond our own, he noticed that they were all moving away from us. More fascinating still, the farther a galaxy was, the faster it appeared to be speeding away. This led to a straightforward yet profound equation. If v represents the velocity at which a galaxy recedes and d is its distance from us, then v is directly proportional to d. This relationship birthed what we now call the Hubble constant, a figure that lies at the heart of contemporary cosmic dilemmas. The significance of the Hubble constant cannot be overstated. It measures how quickly a galaxy moves away from us per megaparsec of distance. To put this into perspective, consider a megaparsec as a unit of astronomical measurement, approximately equivalent to 3.26 million light-years. Let's visualize this with a simple example. Imagine two galaxies. Galaxy A is 1 megaparsec away, and Galaxy B is 2 megaparsecs distant. If the Hubble constant is 70 kilometers per second per megaparsec, Galaxy A would be receding at 70 kilometers per second. Galaxy B, being twice as distant, would recede at twice the speed, 140 kilometers per second. This calculation, 2x70, 270 chem/s, unveils a universe that is not only expanding, but doing so at an accelerating pace. This discovery, first glimpsed by Hubble and now further probed by the James Webb Space Telescope, continues to be a cornerstone of cosmological research, holding keys to the universe's ultimate fate. As Edwin Hubble peered into the vastness of space, he uncovered not just galaxies retreating from us, but a universe stretching at an increasing rate. This phenomenon isn't due to galaxies physically moving through space. Instead, it's the fabric of space itself that is expanding. The Hubble constant, then, is our measure of this expansion speed. Now, you might wonder where the complication lies. It seems straightforward, right? Just measure the distance to a galaxy, d, and its recession velocity, v. Plug those values into a simple equation, and voila! You have the Hubble constant. If only it were that simple. Determining how fast a galaxy is moving away is relatively straightforward. We observe its redshift and calculate the velocity from there. However, accurately gauging the distance to a galaxy millions of light-years away, that's where astronomers hit a snag. Enter the ingenious method devised by astronomers, the use of Cepheid variables. These are a special class of stars known for their consistent pulsation cycles. They brighten and dim in a very predictable pattern. In the early 1900s, Henrietta Swan Leavitt studied many of these stars in the Magellanic Clouds and uncovered a pivotal relationship between their pulsation periods and luminosities. The rate at which a Cepheid star pulsates correlates directly to its intrinsic brightness. Put simply, the longer the pulsation period, the brighter the star. This breakthrough allowed astronomers to map out distances to far-off galaxies with unprecedented accuracy, shining a light on the vast, stretching cosmos. Imagine unlocking the distance to a galaxy nestled millions of light-years away. All it takes is understanding the rhythm of a single star within it. This is the power of Cepheid variables, stars whose pulsations illuminate the vast scales of the universe. If you're ready to embark on this cosmic calculation, here are the 3 essential steps. First, we observe the pulsations. Astronomers pinpoint a Cepheid variable in a distant galaxy and meticulously track how long it takes the star to complete one full cycle of brightening and dimming. Since a star's pulsation period is directly linked to its luminosity, this timing helps us establish the star's true brightness or absolute magnitude. For instance, if a star's cycle lasts 30 days, its absolute magnitude might be around 4.85. The second step is to compare the apparent and true brightness. While the absolute magnitude tells us how bright the star really is, its apparent brightness, how bright it appears from Earth, is what we can measure with telescopes. Suppose the star's apparent brightness is 24. Here's an intriguing tidbit. The faintest stars visible to the naked eye have a brightness of about 6, meaning the star in our example is roughly 16 million times fainter than what the unaided human eye can detect. The third and final step involves the magical brightness-distance relationship. This is where cosmic alchemy comes into play. With a fundamental principle of astronomy in hand, if you know a star's true brightness and can measure its apparent brightness, you can calculate just how far away it is. This celestial method opens a window to not only the distance of galaxies, but also the broader mechanics of our expanding universe. To unravel the mysteries of cosmic distances using a singular star, astronomers follow a captivating process. It begins with the observation of a Cepheid variable star's pulsation period within a distant galaxy. This rhythmic brightening and dimming sequence is the first clue in our cosmic detective story. By applying the well-established period luminosity relationship, we can determine the star's true brightness, also known as its absolute magnitude. Next, we measure the star's apparent brightness from Earth using powerful telescopes. This step is crucial as it reveals how the star's light diminishes over astronomical distances. Finally, with the absolute and apparent brightness at hand, astronomers deploy a straightforward yet profound astrophysical formula known as the modulus equation. This calculation pinpoints the star's distance, which, in our case, turns out to be a staggering 5.9 megaparsecs. Using this method, even a single star can reveal the distance to the galaxy it inhabits. Apart from Cepheid variables, astronomers also harness the luminosity of type Ia supernovae to measure distances to their host galaxies. While Cepheids are ideal for mapping distances within tens of megaparsecs, type Ia supernovae extend our reach to hundreds of megaparsecs. Sometimes, astronomers blend these two methods to cross-verify distances, enhancing the accuracy of their cosmic map. Through advanced technology and meticulous measurements, astronomers have converged on a Hubble constant of approximately 73.4 km/s per megaparsec using Cepheid variables. But the certainty of this number remains under scrutiny, prompting scientists to continuously test and refine it against cosmological models, ensuring our understanding of the universe remains as precise as the universe itself is vast. If the results matched, it would confirm our understanding of the expanding universe. However, if the values didn't align, it would suggest a fundamental flaw in our grasp of the cosmos. Enter an independent method involving the Big Bang's relic, the cosmic microwave background, CMB. The CMB is the universe's oldest light, a faint glow left over from the Big Bang that permeates the entire cosmos. It offers a snapshot of the universe just 380,000 years after the Big Bang, long before stars and galaxies formed. Unlike the cosmic distance ladder, a series of steps astronomers use to measure distances in the universe measurements from the CMB provide a unique way to cross-check results obtained from Cepheid variables and supernovae. By mapping the tiny temperature fluctuations in the CMB across the sky, using satellites like WMAP and the Planck spacecraft, astronomers can glean insights into the density variations of the early universe. These fluctuations are intricately linked to various cosmological parameters, including the universe's expansion rate. When astronomers calculated the Hubble constant using these two methods, they expected to find the same value. However, the results were startlingly different, hinting at a deeper mystery in our understanding of the universe. Then came a surprising twist. The value of the Hubble constant derived from the CMB method was around 67 km/s per megaparsec, noticeably lower than the value obtained using Cepheid variables and supernova. While the discrepancy might appear small, it is statistically significant and beyond the expected margins of error for such precise measurements. This gap is known as the Hubble tension, representing the biggest crisis in cosmology today. The essence of this crisis lies in the Kahn telescope, expecting its advanced infrared capabilities to resolve the issue. However, the new results only confirmed their worst fears. The observations revealed that Cepheid variable stars, often located in densely packed stellar regions, were not the source of the discrepancy. Instead, the tension between the local and early universe expansion rates persisted, suggesting a deeper, underlying problem with our current cosmological models. In other words, Cepheid variables often appear in crowded star fields, complicating the measurement of their brightness and affecting the accuracy of distance estimations. Take, for example, a specific Cepheid variable identified in NGC 5584. In images captured by Hubble's Wide Field Camera 3, this star appears as a fuzzy red spot surrounded by numerous other celestial bodies. With its superior infrared capabilities, the James Webb Space Telescope offers a clearer view. The same Cepheid variable, when observed by Webb, stands out more distinctly, isolated from neighboring stars, thus allowing for more accurate measurements. Scientists observed several Cepheid variables in two key galaxies, NGC 4258 and NGC 5584. NGC 4258 is relatively nearby, with a well-established distance, while NGC 5584, which hosted the type Ia supernova SN 2007 AF, is a more distant galaxy, rich in Cepheid variables. Over 320 Cepheid variables from these galaxies were analyzed using both Hubble and the James Webb Space Telescope to compare their capabilities. In their study, researchers mapped the positions of these variables, particularly in NGC 4258, with periods ranging from 18 to 41 days. The images from Hubble are marked in the first row of the research figure, showcasing the differences in observation clarity between the two telescopes. This comparative analysis underscores the enhanced precision of the James Webb Space Telescope, providing clearer, more isolated views of Cepheid variables, and thus refining our understanding of cosmic distances and the ongoing Hubble tension. In the research, Hubble's images are highlighted in black, while those from the Webb telescope are in magenta. The Hubble images appear crowded, whereas Webb's higher resolution provides a clearer, less cluttered view. This clarity is why the research paper on this study is aptly titled "Crowded No More." Image patches from both telescopes showcasing Cepheid variables in NGC 5584 with periods ranging from 39 to 43 days reveal this distinction vividly. Using these observations, the period magnitude relation was established for both galaxies, as depicted in the two panels. The red data points, derived from Webb's filter, and the gray dots, representing Hubble's observations, tell an intriguing story. This comparison reveals that the red data points follow the same trend as the gray ones. However, there's a noticeable reduction in standard deviation for both galaxies in the Webb data points. A lower standard deviation means less error, showcasing Webb's superior precision. To validate these findings, the team observed larger samples of Cepheid variables and supernovae in a total of 6 galaxies. Remarkably, the results were consistent, reinforcing the accuracy and reliability of the James Webb Space Telescope's measurements and confirming the persistent tension in our cosmological models. With these observations, the team confidently ruled out measurement error as the cause of the Hubble tension. The James Webb Space Telescope has validated the Hubble constant's value, confirming that this discrepancy isn't due to technological limitations or measurement uncertainties. Instead, it highlights a gap in our fundamental understanding of the universe. Now that the James Webb Space Telescope has confirmed the Hubble tension, we face a profound mystery. Are we making mistakes in our distance measurements? Is there a flaw in our understanding of the cosmic microwave background? Or could both values be off due to an unknown factor? Resolving the Hubble tension is critical for 3 reasons. First, it challenges us to test the standard model of cosmology. The Hubble tension might reveal a flaw in the lambda cold dark matter model, our current best framework for understanding the universe. This model incorporates the fundamental components of the cosmos, but the tension suggests we might be missing something crucial. Understanding and resolving the Hubble tension could lead to groundbreaking discoveries, pushing the boundaries of what we know about the universe and potentially unveiling new physics. As we continue to explore this cosmic enigma, the answers we seek could transform our comprehension of the cosmos forever. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.